The question is before you. The numerical problem before you, I'm going to read that one. Compare the RMS speed of hydrogen molecule at 127 degrees Celsius with RMS speed of oxygen molecule at 27 degrees Celsius. See comparison of hydrogen with oxygen. Given that molecular masses of hydrogen and or oxygen is 2 and 32 respectively. So once again, compare the RMS speeds of hydrogen molecules at 127 degrees Celsius and with the RMS speed of oxygen molecule at 27 degrees Celsius. Given that molecular masses of hydrogen and oxygen are 2 and 32 respectively. So how to get the answer? Once again, we are going to utilize the same equation, that is RMS velocity, that is root mean square velocity is equal to under root of 3 RT upon M. Let us start with this one, but before that one, what exactly is the data which is given? Here it is the problem number, here it is 16. Problem number 16, and here the data is before you. Data, here the temperatures are given. What exactly the temperatures which is given? T hydrogen is equal to 127 degrees Celsius, and for the oxygen, sorry, it is what exactly it is given? Yes, oxygen, that is O2, which is given by how much? 27 degrees Celsius. 27 degrees Celsius. So accordingly, I am going to substitute now. If these factors are given, and what about the next one? The molecular masses of hydrogen and oxygen it is given. Means molecular masses of hydrogen, that is H2, which is given by how much? It is hydrogen is 2 and oxygen is 32. So molecular masses of oxygen, it is equal to 32. So all these factors are given. Now I am going to write the formula for that one. And what we are going to calculate? What to calculate? Compare the RMS speeds. Means here, C RMS for what? Here I am going to compare, means comparison of what? Hydrogen and oxygen. Comparison of hydrogen and oxygen means hydrogen H2 upon CRMS O2. The question mark, this I want to compare. So how to compare? We know very well the formula for that one, that is C RMS is equal to under root of 3 RT upon M. So this is the basic equation, and accordingly I am going to get the answer by substituting all the values. We know the T, we know the M. So accordingly, CRMS for hydrogen, which is given by under root of 3 RT. Here T hydrogen upon mass of hydrogen atom. So molecular masses of hydrogen atom. So substituting that value, here it is under root of 3 R. Here it is temperature. Here I am going to convert that into 127 plus 273. How much? If I am going to add, it comes out to be 400 Kelvin. 400 Kelvin. What about this? This is 27 plus 273. That comes out to be 300 Kelvin. If we substitute here for the hydrogen, it is 400 into 400 upon, here it is mass of hydrogen atom is how much? 2. Here I have substituted 2, but before that one, if I am going to cancel this one, the answer will be, here it is 3 R into, here it is 200. So C RMS for oxygen, which is given by under root of, here it is 3 R T O2 upon M O2. Substituting values, 3R as it is. That's why I am not going to multiply this factor, because 3R get cancelled if we take the ratio of these two, into what about the temperature for the oxygen? It is 300 divided by what about this? This is 32. 32. If we compare these two, or I'm going to solve these two, or as it is I'm going to put this and get the ratio of these two, then I'm going to get CRMS hydrogen upon CRMS oxygen. It is equal to, here it is under root of 3R into 200 upon, here it is under root of 3R into 300 upon 32. If we compare both, are going to divide. 3R get cancelled, these two zeros get cancelled. If we take the reciprocal of that one, nothing means it is divided by 1. If we take the reciprocal of that one, in under root of 32 upon 3 into, here it is 32 into 3, as it is 2 by 1. So what about this? It is given by, the answer it is 32 into 2, that is 64. So under root of 64 upon 3. This can be taken outside the square root. So 8, and as it is under root of 3 remains in the square root. So as per this one, CRMS hydrogen upon CRMS oxygen is equal to 8 upon under root of 3. So going to compare that, CRMS hydrogen as to CRMS oxygen is equal to 8 as to under root of 3. This is your final answer. Here is the problem number 17 before you. Find the kinetic energy of 5 liter of gas at STP, standard temperature pressure. Given standard pressure is 1.013 into 10 raised to power 5 Newton per meter square. Then we'll have to find out the kinetic energy. We know that in terms of pressure, the kinetic energy formula, we'll have to remember that what exactly it is given, that we are going to write first. Here it is the problem number 17. The pressure, standard pressure, it is given 1.013 into 10 raised to power 5 Newton per meter square. Now volume it is given, that is 5 liter. 5 liter means how much? So accordingly I am going to write that 5 into 10 raised to power minus 3. Here it is meter cube. So this is given and we'll have to find out the kinetic energy. So we'll have to find out the kinetic energy which is given. Yes, absolutely. Now how to get the kinetic energy in terms of this one? Even if the STP it is given, we know that at standard temperature pressure T is equal to 273 Kelvin. So but here it is not concerned to the temperature. So I am going to write that kinetic energy is equal to 3 by 2 PV. This is the formula I am going to utilize. I am going to get the answer for this. So here it is 3 upon 2 into P means 1.013 into 10 raised to power 5. And what about this? It is 5 into 10 raised to power minus 3. So all these values here I am going to, after solving that, it is we say 2.5, half of that 2.5. So 3.039, here it is 3.039 into 2.5 into 10 raised to power, here it is 2. If we are going to solve this one, the answer comes out to be 7.5. See, there is a multiplication. and we know multiplication very well. 3.5975, it is the answer into 10 raised to power 2 as it is. Here the book, it is given somewhat different answer. Here it is somewhat different, we say, answer we are going to get from the Bal Bharati book. But as per our solving is concerned, or our formula it is concerned, and all these precautionary measures are concerned, our answer is this one. So there is some sort of, I think, there is some sort of correction in that Bal Bharati book. From the Bal Bharati book, answer is 0.75. Here it is the answer, 0.7597. This is the answer. It is expected, but our answer is 7.59. Okay, 75. This is our answer, and as per our knowledge, this answer is correct one. Now we have the problem number 18. Let us read this one. Calculate the average molecular kinetic energy. Calculate average molecular kinetic energy, that is 1 per kilomole. See, it is not, we say, per mole. It is per kilomole. So we need to multiply it by 3 so as to convert that into per kilomole. Okay, we'll have to remember that one. Number 2, per kilogram, and number 3, per molecule of oxygen at 127 degrees Celsius. Given that molecular weight of oxygen is 32, molecular weight of oxygen is 32, and R is 8.31 joule per mole Kelvin, and Avogadro's number, it is 6.02 into 10 raised to power 23. Here it is 6.02 into 10 raised to power 23 molecules per mole, and accordingly we are going to get to 3, that is kinetic energy per kilomole, kinetic energy per kilogram, and kinetic energy per molecule. So accordingly we are going to get the 3 formulae. And what about the data which is given, that I am going to write here. What it is given, the temperature it is given, the temperature is 127 degrees Celsius. Before that one I am going to give the number, that is 18. So what about the data which is given here? I am going to write that data. Here it is. That temperature T is equal to 127 degrees Celsius. That means 127 plus 273. This 273, if it is added in 127, it is get converted into Kelvin. So it is 400 Kelvin. So this is about the temperature. What about the next factor which is given here? It is the molecular weight of oxygen. It is given, that means M oxygen. It is given how much? 32. We know very well. Now the next is Avogadro's number. It is given, that is Avogadro's number denoted by the symbol Na, N suffix A. That is given by how much? 6.0. It is somewhat different number it is given. So we'll have to take this 6.02 into 10 raised to power 23, and including that one we are going to write the unit also, molecule per mole. Molecule per mole. Okay. And what about the next? This is Avogadro's number. Here R is also given. R is 8.31 joule per mole Kelvin. It is given. Joule per mole Kelvin it is given. So accordingly I am going to write this joule per mole Kelvin. So accordingly this is your R, Na and T. What about the first thing that we are going to calculate? That is kinetic energy per kilomole. Kinetic energy per kilomole. So this is the first factor that we need to calculate. Second one, kinetic energy per kilogram, means kinetic energy per kilogram means per mass and per molecule. Third one, kinetic energy per molecule. So we'll have to divide that by with a Avogadro's number, right? That is a molecule. Yes, absolutely. So the first thing I'm going to write, the first, that is kinetic energy per kilomole. Just we'll have to remember that here it is once again 1 kinetic energy per kilomole, and the next is we say kinetic energy per molecule, sorry, kinetic energy per mass, we say mass means per kilogram, and kinetic energy per molecule. Now we are going to one by one, we are going to solve that one. So here it is 3 by 2 kinetic energy per kilomole, the formula it is 3 by 2 RT, the basic equation. Either maybe going to be write the PV, but here R we know very well, and T also we know very well. That's why in terms of R and T it is expressed into 10 raised to power 3. Why it is so? This gives us a kinetic energy per kilomole. We'll have to convert that. Only mole, that time don't need to take this 10 raised to power 3. But here kilomole, and that's why 10 raised to power 3 we are going to take. So one by one I am going to substitute this. 3 by 2 RT, R is how much? 8.31, okay, 8.31 into temperature, that is 400 Kelvin, into 10 raised to power 3. So here it is cancels with this is 200. So 3 into 8.31 into here 10 raised to power 2, or here it is 200. Instead of 200 I am going to write 2 into 10 raised to power 2 into 10 raised to power 3. So 3 plus 2, 5. In multiplication powers get added, and 3 into 2, 6. Means 6 into 8.31 into 10 raised to power 5. So the final answer I am going to write directly, that is 4.986 into 10 raised to power 6 joule. This is the answer for this. Now this is about the first, that is kinetic energy per kilomole. So the next I am going to write, it is kinetic energy per kilomole. Okay, this is about this. And next is we say kinetic energy. This is over. This is we are going to take kinetic energy per mass. Kinetic energy per mass, which is given by 3 by 2 RT upon M. But this is about to take the molecular mass of oxygen, because we are going to take the oxygen, and that's why I'm going to substitute all the terms. 3 by 2 into here 8.31 into T, that is 400, upon molecular mass, that is 32. After solving this, here it is 200. And what about the next one? Here it is 8.31 into 100 means 10 raised to power 2. What about this 2? Here it is 2 with a 32. If we are going to divide that one, here it is 3 divided by 2, but 2 already get cancelled. Only 3 factor it is remain. 3 into this 2, if it is cancels with this one, it is comes out to be 16. So after solving this, 3 into 8.31 into 10 raised to power 2, okay, 10 raised to power 2 divided by 16, the answer is, directly I am going to write the answer, that is 1.56 into 10 raised to power 2, 1.56 into 10 raised to power 2 joule. This is your final answer for this. This is about the kinetic energy per mass. Now we are going to take the third term, that is kinetic energy per molecule. So kinetic energy per molecule, that means we need to divide whole terms molecule 3 by 2 RT upon ENA, that is Avogadro's number. So if we divide that 3 by 2 into R, that is 8.31 into 400 upon Avogadro's number, that is 6.02 into 10 raised to power 23. If we are going to divide this, I am going to get the answer, that is 600 into 8.31 into 10 raised to power 23. Here minus 23 if it is taken in the numerator. And what about this 6.02? If you need to solve this, I am going to get the answer, that final answer is 8.28 into 10 raised to power minus 21 joule. This is your answer. See one by one: kinetic energy per kilomole, kinetic energy per mass, and kinetic energy per molecule. Only change is this one. Instead of only kinetic energy per mole, here kilomole I need to multiply it by 10 raised to power 3. This criteria we will have to remember, or this fact we will have to remember. Let us read the question number, or the numerical problem number 19. Calculate the energy radiated in 1 minute by a black body of a surface area 100 centimeter square when it is maintained at 227 degrees Celsius. What the factors which are given, that I am going to write. Here it is 19. Data. How much is the area? Area is 100 centimeter square. So we know that centimeter to meter, 10 raised to power minus 2, square of that one 10 raised to power minus 4, that means 100 into 10 raised to power minus 4 meter square. Once again, this 100 means how much? 10 raised to power 2, that means 10 raised to power minus 2 meter square is the area, is the conversion factor. So accordingly, what about the temperature? The temperature, it is given 227 degrees Celsius. 227 degrees Celsius. So 227 plus 273, so as to convert that into Kelvin, it comes out to be 500 Kelvin. So this is your 500 Kelvin. What about the next? So here it is, we need to calculate what? Within a time t, 1 minute. 1 minute means how much? That is 60 seconds. Once again, where exactly the 1 minute? Calculate the energy radiated in 1 minute. Energy radiated in 1 minute. So what about the formula? We know that amount of energy by which body? That is the main thing. That is black body. We know for the black body, amount of energy radiated per unit area per unit time is directly proportional to fourth power of absolute temperature. And we know very well, we are Q upon T, Q upon AT is equal to sigma into T raised to power 4. What about this sigma? That I am going to write. Sigma is a constant. What about that one? It is a Stephen's constant. 5.67 into 10 raised to power 8. What about that 8? That is main thing, which is given here. Absolutely, it must be given in that one. Joule per, we know very well, joule per Kelvin, joule per Kelvin raised to power 4 into meter square second. This factor must be given. So all these are known. This is minus 1. So sigma, we'll have to remember 5.67 7 into 10 raised to power minus 8 joule per second meter square into Kelvin raised to power 4. So all these values are known. Just we need to calculate Q, because Q is equal to A into T into sigma into T raised to power 4. So substitute all that one by one. 10 raised to power minus 2 area, time 60 seconds, sigma 5.67 into 10 raised to power minus 8. What about the temperature? Temperature is 500 Kelvin, or I'm going to write 5 into 10 raised to power 2 raised to power 4. So Q, if collecting the power of 10, so what exactly is this one? So here I'm going to collect power, but I'm going to write it in the last. That is 5.67 into 5. 5 into 5 into 5 into 5 into 10 raised to power minus 2 into 10 raised to power minus 8 into 10 raised to power. Here it is 10 raised to power 2 raised to power 4 means 8. That means these two get cancelled. What about the remaining factors? If I am going to multiply this total factor, I am going to get the answer, that is 2126.25. That is the final answer. Obviously Q means it is in joule. Energy radiated means energy which is measured in joule. This is the expected answer. Here it is the last problem before you, that is problem number 20. Energy is emitted from a hole in an electric furnace at the rate of 20 watt. See, watt is the energy radiated within a given time. So dQ upon dt, we can term it as a 20 watt. When the temperature of the furnace is 727 degrees Celsius, means 727 plus 273, that means 1000 Kelvin. That means 1 into 10 raised to power 3 Kelvin I am going to write. What is the area of the hole? What about the Stephen's constant? Somewhat it is changed, it is given, that is 5.67. Instead of that one, 5.7 into 10 raised to power 8 joule per second meter square Kelvin raised to power 4 it is given. So one by one I am going to write that, and accordingly I am going to calculate the area of that hole. From that one, the energy it is emitted or coming out. So let us start with this 20 data. What about the temperature? The temperature is T. How much? 727 degrees Celsius means 727 plus 273. That comes out to be 1000 Kelvin. This is about the temperature. What about the, we say, amount of heat radiated per unit time, which is given by, it is 20 watt. And what about the Stephen's constant? It is given already, it is given, that is how much? Somewhat change it is given, that is 5.7, not the 5.67. Okay, instead of that one, only 5.7 into 10 raised to power minus 8 joule per second meter square Kelvin raised to power 4 it is given. So instead of writing these units, always there is a small gap between these two, means second meter raised to power means meter raised to power 2 temperature, or Kelvin raised to power 4. Here Kelvin raised to power 4. Always there must be some sort of gap between these two. So here it is. And what about this area? Area it is given. So it is seems to be considered black body. So E is equal to 1. So here it is the formula for the dQ upon a dt is equal to sigma into E into A into T raised to power 4. But here E is equal to 1 for we say black body. Black body, E is equal to 1. So we are going to extend one more step. dq upon dt is equal to sigma into a into t raised to power 4. So a is equal to dq upon dt upon sigma into t raised to power 4. So a area I need to calculate. dq upon dt is 20 watt. So 20 watt upon, we are going to write sigma, that is 5.7 into 10 raised to power minus 8 into 1000 raised to power or 10 raised to power. I'm going to write this as a 10 raised to power 3 Kelvin. So 10 raised to power 3 raised to power 4, that means 12. If we are going to solve this one, 20 upon, here it is 5.7 into 10 raised to power minus 8 into 10 raised to power, here it is 12, that means it is plus 4. It is taken in the numerator, it is minus 4. So area, it comes out to be the final answer, that is 20 into 10 raised to power plus 4. It is taken in numerator, it is minus 4 upon 5.7. If we solve that one, it comes out to be 3.5 something, 3.5 into 10 raised to power minus 4 is the answer. Obviously it is in meter square. This is your final answer if we solve this one. So this is your problem number 20. We will continue the next problems in the next session. Thank you.